critical temperature for superconductors is the temperature at which the electrical resistivity of a metal drops to zero. The transition is so sudden that it appears to be a transition to a different phase of matter. This superconducting phase is described by the BCS theory. Cooper realized that the atomic lattice vibrations were directly responsible for this strange phenomenon. They forced the electrons to pair up into teams in order to pass all of the obstacles. This condensation of electrons is known as the Cooper pairs. Cooper and his colleagues knew that for electrons to come together, there must be an overwhelming attraction overcoming the normal repulsion. This was explained through the discovery of phonons, quanta of sound waves present in the lattice as it vibrates.
Let's look a little deeper into the workings of superconductivity. In a metal lattice, the electrons in the outermost shell of the atoms are delocalized, causing the atoms to be ionized, and therefore, when the electric current, which are essentially electrons, passes through the lattice, they get attracted by the positively charged ion. Vice versa, the positively charged ions are attracted to the electrons, causing a delayed distortion to the shape of the lattice. It is important that the lattice movement is delayed because it prevents the electrons from colliding with the positive ions, which would make them lose energy. As the lattice comes together, it forms a region of enhanced positively charged ions, which draws another electron before it springs back to its original shape.
When electrons are linked together in pairs, they move through the superconductor in an orderly fashion. This cycle continues and produces several electrons interlocked together. Despite Pauli's exclusion principle, stating that two electrons with the same quantum number cannot come together, the electrons in a superconductor take the characteristic of a boson. Bosons are particles which have integer spin. Therefore, they are not constrained by Pauli's exclusion principle. Thus, the BCS theory successfully shows that electrons can be attracted to one another through interactions with the lattice. This occurs despite the fact that electrons have the same charge. The condensed electrons are pulled together by the attraction with the positively charged ions without a collision. The electron pairing is favorable because it has the effect of putting the material into a lower energy state.
There are two types of superconductors, type 1 and type 2. A type 1 superconductor is usually made of a cool metal, which when cooled below its critical temperature exhibits zero electrical resistivity and displays perfect diamagnetism, meaning magnetic fields cannot penetrate it while it is in a superconducting state.
A type 2 superconductor is made from alloys. Besides being mechanically harder than type 1 superconductors, they exhibit much higher critical magnetic fields. They usually exist in a mixed state of normal and superconducting regions.
So what's the big deal about superconductors? What do we get out of them in our everyday lives? Well, superconductors have the potential to completely change our lives economically, technologically, and ecologically for the better. For example, magnetic levitation is a great application of superconductors. In order to understand magnetic levitation and suspension, it is first important to identify some key properties of superconductors. Firstly, we need to define the term Meissner effect, which describes the property of superconductors to repel magnetic fields. Since the electrical resistance is zero, supercurrents are generated in the material to exclude the magnetic fields from a magnet brought near it. The currents which cancel the external field produce magnetic poles which mirror the poles of the permanent magnet, repelling them to provide the lift to levitate the magnet. This is known as the flux trapping effect. The suspended magnet can be moved or even spun rapidly, and the levitation currents will adjust to keep it in suspension.
This remarkable property of superconductors has led to the creation of maglev trains, whereby the trains float on a frictionless path, creating a fast and energy-efficient mode of transport. Improvements in the public transportation system using superconductors can significantly reduce the amount of carbon dioxide emitted into the atmosphere, decreasing the ecological footprint of millions of people. It is theorized that this new type of train will emit about 1/3 of carbon dioxide. Subways are about to get a whole lot more crowded.
Moreover, superconductors can perform life-saving functions in the field of biomagnetism. Most MRI systems use a superconducting magnet, which consists of many cords of wire through which a current of electricity is passed, creating a magnetic field. Maintaining such a large magnetic field requires a good deal of energy, which is accomplished by superconductivity kept in liquid helium insulated in a vacuum.
created using Powtoon.